Okay, so in the last video, which is part one of Statistics for Psychologists, we discussed two hypothetical sets of results from the famous Milgram experiment from the 1960s. So if you haven't watched that video, I suggest you go and watch it now. But anyway, assuming that you have, the two results, and I'll repeat, they are hypothetical, they're only for educational purposes here. Let's just remind ourselves of them. So in the 1960s experiment, we found that the mean was 7, that the standard deviation was 1.2, and the participant who we were interested in, their Z-score was 3.4. And then we calculated in the 2023 experiment that the mean was 6 and the standard deviation was 2.28 and the participant Z-score was 1.32, and we did some fairly basic comparisons between the two. So now what we want to do is we need to formalise a little bit some of the statistical definitions that we discussed in the last video. So first of all, what we need to do is we need to discuss the difference between the population and a sample. Now, let's imagine in our 2023 experiment we had 1,000 students who were going around electrocuting or fake electrocuting this poor person in the room next door. If we had 1,000 students, so we would sort of say, you know, we got S1 and let's say that his score was a 7, and we got S2 and let's say that he moved the dial to a 3, and S3 he moved the dial to an 8, blah blah blah, and we got to say S10 and he moved the dial to a 9, and then we got S11, blah blah blah, all the way to S20, and we go down all the way to, for example, you know, the 1,000th student, which was S991, and he moved the dial to 8, and all the way to S1000, student 1,000, and she moved the dial to a 4. That is our population. Now, most of the time we don't bother to do the statistical analysis on the entire population. What we would do is we would do it on what's called a sample. So, for example, we might choose this as a sample. So we might only look at student number 1, student number 11, student number 21, student number 31, all the way down to student number 991. So that would be a sample of 100 out of the 1,000. Now, formally, if we are going to use the entire population, then the variance, which we discussed in the previous video, the variance of the population is calculated by the following formula. Sum of x minus the mean squared over n. Now that variance is denoted when it's a population, so let's just call that that's variance population. So that means we're going to use all 1,000 students, the variance of the population, and it's denoted as sigma squared. Now, when we use the entire population, n is the number of people in the population, i.e. 1,000, the population size. M, by the way, a lot of people actually use Greek letter mu for the mean, so don't get confused about that. It's exactly the same whether you use M or mu as the mean. So this is the variance of the population, and the standard deviation if we use the population. So the standard deviation, which is denoted as sigma of the population, is the square root of the variance, which we've just calculated, of the population. Now, if we are not going to use the population, but we're going to use a sample, the formula is very slightly different, but it's only very slightly different. But it's just worth knowing. So the variance of a sample, so let's say, for example, that we were just going to use 100 students or even 10 students or 5 students, but somehow we were only going to use and analyse a sample of the 1,000 students who took the test. The variance of the sample is actually denoted by a slightly different letter. It's s squared instead of sigma squared, and that equals the sum of x minus m squared over n minus 1. where n here is the sample size. So it's almost identical, except when we are doing the variance of the population, we take the entire population. When we are doing the variance of a sample, we take the sample size minus 1. And then the standard deviation of a sample, which is denoted by S, is again the square root of the variance of the sample. So it's only a small thing, but it is important. So now let's move on. So what we're going to do now is have a look at what's called the distribution. So we've got our 1,000 students, and if we did some sort of tally chart or whatever as to what dial, let's imagine that we have the dial 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and how many students moved the dial to 0 might be sort of, 19 of the 1,000 or whatever, and how many moved it to 1 might be 27, and how many moved it to 2 might be 46, blah, 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 blah. Now we know that the mean was 6, so we know that probably most of them will have been somewhere around 6, so maybe sort of 127 were 6, and then maybe how many were 9 were sort of 46, or how many were 10 were 22, how many were 12 possibly just 1 or whatever. This tally chart here is the distribution which we can draw on a graph. Now basically, normally, and certainly not always, but normally, and we can assume for the sake of argument here, that the graph will look a sort of a normal distribution, something like that, where this here represents the mean, and this is the number of participants, and this is the dial number. So this tells us, for example, that if we have here the dial 9, that this many students here move the dial to 9, and this many students move the dial to 7, etc., etc., etc. Now, why this becomes very interesting is if we start to look at standard deviation and this normal curve. So let's imagine that our normal curve for the 2023 experiment, using the entire population of 1,000 students, let's imagine that it does actually look like that, where here is moving the dial to 12, here is moving the dial to 0, and again here is the number of participants who moved the dial to whatever number, and here we've got the mean, which we know from previous is 6. Now, where the standard deviation comes in here is that we know from the previous video that the standard deviation of the 2023 experiment was 2.28. What we can put this onto the graph. So if we add 2.28 to 6, we get 8.28, which is here. And if we take away 2.28 from 6, we get 5.72. 3.72. And this represents here the mean, which we can put as mu, plus the standard deviation, one standard deviation, which is sigma, and this represents here the mean minus one standard deviation. If we carry on by another standard deviation, i.e. we add another 2.28, so that would get us to 10.56. That is the mean add 2 standard deviations. And then if we take another 2.28, we get the mean minus 2 standard deviations, which is 1.44, which is the mean minus 2 standard deviations. And what we're getting here is this here is actually equal to and identical to what we talked about in the previous video, i.e. the z-score. So somebody who has a z-score of 2, for example, what that means is that their score was equal to the mean add 2 standard deviations. So their score was here. If they have a z-score, for example, of minus 2, then that means that their score was equal to the mean minus 2 standard deviations, which means that their score was here. So this is directly comparable to the z-score. And by the way, if their z-score is 0, then that means that they moved the dial to 6. A z-score of 0 by definition means that you scored the mean. Now, just adding one more thing to this, it actually has a lot of predictive power. Once we have our distribution chart of our 2023 results, and let's just redraw this distribution chart here, which is called a normal distribution, by the way. It doesn't have to be normal, but normally we find that they are normal. So we have mu equals 6. So mu plus, that's the mean, plus 1 standard deviation is here. And mu minus 1 standard deviation is here. And mu minus 2 standard deviations is here. And mu plus 2 standard deviations is here, which are the z-scores. So they correspond to the z-scores of minus 2, minus 1, 0, 1, and 2. They're the z-scores. We can actually predict what the probability of somebody getting various scores are. Because the distribution is normal, we know that 34% of participants will be in this area here between the mean of 6 and the mean plus 1 standard deviation, which was 8.28. We also know that 34% will be in this. 34% will be here. So 34% of participants we can predict will have moved the dial between 6 and 6 minus 1 standard deviation. Or, using z-scores, we could also say that 34% of our participants will have a z-score of between 0 and 1. And we can say that 34% of our participants will have a z-score between 0 and minus 1. We can also say here, let's use another colour, we can also say here that 13.5% and 13.5% will have z-scores of between minus 1 and minus 2, and 13.5% of our participants will have a z-score of between 1 and 2. And we can carry on between 2 and 3. The percentage of people who would have that z-score between 2 and 3 is 2.35% here and 2.35% here. And then we're left with a tiny, tiny fraction who are have a z-score of either more than plus 3 or less than minus 3. Only 0.3% of the entire population will have a z-score of more than 3 or less than minus 3, which, if your population is 1,000, then that will only be 30 of the participants will have a z-score of between either more than 0.3 or less than more than 3 or less than minus 3. And if we just go back just for a second to our z-score of the participant in the 1960s, and remember this is hypothetical, this was just made up, but our participant had a z-score of 3.4 in the 1960s. That is above 3, which means that the probability of one of the participants in the 1960s getting that, assuming that the population distribution is normal, the probability of that is less than 0.15%. So it's very rare that that particular participant who we were interested in got a score of 3.4, which means maybe further study on that particular participant might be warranted. On our 2023 study, the participant z-score was only 1.32, which if we go back down here, that would be a fairly common score, because 1.2 z-score is basically about here, which means that probably, he's around 50% likely to have a z-score somewhere in that region between 1.2 or minus 1.2. So it's not quite an extreme result as the 1960s experiment. Okay, so that's the end of that video.